Swayam Prabha. Digital India. Educated India.
So let us use the DFS traversal. Fine. Any ideas? So let us recall the DFS traversal. So what will the DFS traversal do? You will start at every vertex, right, which has not been visited, right. So therefore, what does DFS consist of? In the case of a directed graph, so maybe you have forgotten it, right, or maybe you have not forgotten it. There is a visited array, right. So what do? Every time you visit a vertex for the first time, right, you will, let us say you will start at this vertex, you will say I have finished visiting it, you will put 1. So the vertices are numbered 1 to n. Initially nothing is visited, therefore everything was 0. Right. Now what do? You look at the first vertex and you started DFS from that vertex. Let us say from the vertex V1 you started DFS. Right. And for every vertex here you would have associated a value, right, which is the first visit time, right, or rather let me give a standard notation, the start time, the time at which you are starting to explore everything which is reachable from it, right, and the finish time. Fine. It is very clear, right? Imagine that there is a global clock, right. The clock is incremented at every step whenever the algorithm traverses an edge. That is a standard DFS implementation. When you implement DFS, you maintain a variable called a clock. The maximum value for the clock will be twice the number of edges in the graph. Right? You will start the clock at 0 edges, right? The first edge 0, the first edge you visit, the clock will increment by 1, right? And every time you traverse an edge, the clock will keep incrementing. When you return also, the clock will increment. Fine. So therefore, when will you finish this when will you start this vertex? When you, if you let us say this is the edge, this is the 5th edge, right, via which you entered this particular vertex, then S will be 5. At time instant 5, I saw this vertex. Then the interval has been opened and you are exploring everything which is reachable from it, right, all the edges which are reachable from it. Fine. And finally, when you return from each one of them, right, let us say you return via this particular edge, right, whatever be the time, right. So therefore it is, so look at all the edges which are reachable from it, that number, right, will essentially be twice the total number of edges that are reachable from there. Fine. Right. Now we will use, right, so this is what from V1 you will do this, but every time you visit a vertex, let us say I visited V5, then I will go to the visited array and I will put a 1 on the 5th vertex. Fine. So what will DFS actually do? The DFS will actually scan the visited array, right, and it will start a DFS from every vertex which is a 0, right. So therefore the outer loop of DFS has a linear scan of the visited array. Fine. And therefore the running time of DFS is actually n plus 2 times n. Right? Why does the n come? The n comes for inspecting each of these fellows, whether it is a 1 or a 0, 1 or a 0. When it finds a 0, it is going to start exploring the edges which are not visited from there on, which are going out from there on. Fine. And every edge will be traversed only twice by DFS. Once when it walks on it in the forward direction and once when it returns from a function call. Okay. This is the sum total running time of DFS. Apart from that, all those things that Meghna showed, that were shown to you earlier, you are aware of. Right? Fine. So in n plus 2m time, you are now maintaining a DFS traversal data structure. Now, I will give you a little bit of time. Output a ranking, meaning what? You have to output a linear ordering of the vertices, correct? So can you output a linear ordering of the vertices? So let us take a simple graph, right? When you see the example, maybe you will get the idea. Let us take this graph. It is a nice looking DAG, very nice, simple looking DAG. So if you do a DFS, do you get any back arcs? It is a DAG, no back arcs, right? So let us say I start from this vertex. It's 1, 2, 3, 4, right? So now let me put a double line. So this is a tree arc. This is a tree arc, right? Then I return, then this is a tree arc or a forward arc, fine, sorry, a tree arc. Okay, so just for interest, let me put this, right, fine. So this becomes a forward arc, right. What is this arc? Now you have all this information. Right? Now, how are you, in what order will we print? So let us try, right. So after capturing all the starting time and finish time of every vertex, so let us try a heuristic. So which vertex will you print first? You have to print 1, but why did you print 1? Minimum in degree, right? You print 1 because 1 has minimum in degree, fine, okay. After you remove 1, right, then you will print 2, right, because it is a vertex of minimum in degree, right. Then you will print 4, right. Now you will return, right, then you will print 3, right. Instead, let us do the following. I will print every vertex when I have finished visiting everything reachable from it. Let us try that. I will print 4 first, then I will print 2 because I visited everybody reachable from 2, then I will print 3 because I visited everybody reachable from 3 is visited, then I will print 1. Is this the right order that we want, or is it the wrong order? Just reverse it. Right? Can you come up with a logic as to how you will do this? Exactly. No, that's not correct. You traverse it exactly as you traversed, right, in the increasing order of start times, and as you return, just print the vertices as you return and reverse the list. Because if I went with your answer, I will end up printing 3 first, which is wrong. Right? 3 is finished, right? Well, actually 1 is finished last. Right? Yeah, actually you are right. So this is, so therefore his answer is succinct. It repeats what I said, right? So print in decreasing order of finish times, right, is exactly a topological sort, right. So what he said and what I said are essentially identical. He gave a more succinct presentation, printed in decreasing order of finish times. What I said is you just traverse the tree exactly as you traversed it, right. When you finished visiting a vertex, you print it, right, and reverse the printed list and print that out. That is a topological sorting. The proof that it is a topological sorting is immediate, right? If an edge orientation, then V is and V is visited after U, if V is visited after U, so if it looks like this, that is UV is the orientation and V is visited after U, right? Then V is printed first and U is printed after that, and the list is going to be reversed. So the orientation of UV is right. There are a few cases here, right? If the orientation of UV is orientation, V is visited after U, right? But it's also possible that UV is this orientation, but V was visited before U because of something else. Maybe there was a here, right? In this case, also in our ordering, V would have been listed, right, after U, right, in the output ordering. So the proof of this is actually quite straightforward from the algorithm. But what is the running time? The running time is just n plus 2m, which is the time taken to finish a DFS. And if you wish one more traversal of the whole graph, right, visiting every edge twice again, so it will be n plus 4m. Right. Of course, you can just print out vertices, right, as you finish the traversal. But if you want to actually separate the concepts, because in the analysis we are actually separating the two of them, traversal is one, calculating the start and the finish time is other, and then printing them according to the decreasing order of the finish time. If you want to separate them, then you will get an asymptotic analysis of order n plus 4m. Right? This plus 4m is not necessary, so simply it is just n plus 2m. Again, this 2 is not necessary, it is order n plus m. Fine. So as you can see, just for this very simple problem, right, we have three different algorithms. The first algorithm is just a thought process, which simply says just find the sinks and keep removing them. The second one says sinks are those of degree 0. How do I arrange them in a nice data structure? Right? You can use a heap and pull out the vertices of 0 degree, right, quickly, right, and you will get a n log n plus m. And if you do a DFS, then the log n factor is also gone, and that's a significant improvement. Right? So I'm sure some of you are looking for programming exercises. Here is a very, very interesting programming exercise. Right? Get directed acyclic graphs. Right? I'll tell you in a minute how to generate directed acyclic graphs. Right? Here is the experimental evaluation. This is like you can think of this as your school physics lab or something. Right? The first step for an experimental evaluation of a set of algorithms is, remember that you are not doing an asymptotic analysis, that is over. Right? You want to compare these three algorithms. So what you basically want to do is you want to generate large directed acyclic graphs, right, 100 of them, or if you want thousands of them, right, store them in a directory, and this is called a benchmark data set. Right? So therefore, whenever you do an experimental evaluation, it is important to actually store your benchmark data set so that others who are going to compete with your implementations can test their implementations on the benchmark data set. Right? So this is a very, very important development practice. Right? So you should keep this in mind. Next step, right, is to run the three algorithms run the 3 algorithms and plot, right, the running times. Remember that asymptotically n square plus m, n log n plus m and n plus m. It is quite clear which is the best function. However, the running time of your algorithm depends upon, the real running time of your algorithm will depend upon multiple parameters like the out degree of the graphs that you have generated, right, the number of vertices and so on, right. So therefore, you cannot simply say that you will always choose to do the best asymptotic implementation, right, without worrying about the properties of your experimental data set. Right. Therefore, while we finished a proof that one algorithm is asymptotically better, right, it is not possible to perform an experimental evaluation during a lecture. Right. So really, like a lab exercise, I encourage each of you to program the 3, right, in your favorite programming language, generate large DAGs, right, and like your school physics record book, gather running time information and decide, right, which of the implementations is better, right, and under what conditions, and you can do an analysis. Fine. So therefore, this is a kind of a flow that should be in your mind, right, when you are applying, right, graph theoretic concepts to design algorithms. Right. So let us just look at this. This algorithm, I would say, right, is a very graph theoretic algorithm. You just say that DAGs have sinks, I will remove them one after the other. This one basically, right, is clearly a strong data structure based implementation, data structure based idea. How do I ensure that I don't spend too much time searching for a particular value, especially the minimum? I want to access the minimum very quickly. How do I organize my data? And the last one, right, is really a combination of graph theory, right. For example, where does graph theory get used here? You first observe that there are no back arcs, right, because there are no cycles, right, and then you use properties like every edge is visited exactly twice, right, and every vertex is processed exactly once, because once a vertex is made visited equal to 1, it will never be processed again, right. So it's a combination of both graph theoretic ideas and algorithmic analysis, right, to come up really with a very nice asymptotic implementation. Right. Whereas the experimental analysis is a completely different and very exciting thing, because it depends upon what kind of an operating system you have, right, and many other parameters which I can't really talk about here. So therefore, bad algorithms may actually have better real running times on practical data, right, as opposed to asymptotically large running times. So now we will make a jump among the concepts and we will talk about a parameter called the connectivity of a graph. Right. The word connectivity is already very suggestive to most of us, because if you say that, well, that is a very remote area, there is no connectivity, or the connectivity is very less. Right. This is a phrase that we normally use. So where is your hometown? My hometown is in a very remote area, right? So then immediately the person actually imagines that the connectivity to that area is very limited, right? Which means that there are probably not enough roads, right? So for example, right, so this is a city. There is just a single bridge which is connecting this city to another city. Then you will say that the connectivity of this particular, pair of cities, right, is limited by the connectivity of this particular bridge, right. So therefore, the connectivity is 1. In other words, if you remove one edge, you kill the connectivity, right, of the 2 cities, right. So this is called edge connectivity. Well, there is also a single vertex if you remove, that will kill the connectivity of the two areas, right? And that is called vertex connectivity. Okay, con stands for connectivity, just in the interest of, just not writing connectivity fully. Right? So therefore, given a graph G, right, and a pair S comma T, source and terminus, right, the vertex connectivity of ST, right, is the minimum number of vertices to be removed to disconnect all ST paths. Right? Fine. So for example, if you looked at the strong components DAG, right, that you studied in the previous lecture, right? So if the strong components DAG look like this is one strong component, right? Then there is this edge here, this is another strong component, right? What is the ST connectivity, right? The vertex connectivity of S and T, where S is in this strong component and T is in this strong component. I am just asking you to apply the definition. It is just one. If you remove this one vertex, or if you remove this one vertex, observe that it is well defined. There is a single edge or a set of edges that go from here, right? But let us assume that in this example that I am drawing, there is just a single edge, right? Then the vertex connectivity of S in this particular strong component and T in this particular strong component is 1. You just have to remove this particular vertex. Right? What is the TS vertex connectivity? 0. Right? So therefore, you should remember that there is a bit of asymmetry when you talk about vertex connectivity in directed graphs. Right? But if I remove the edge orientation and consider undirected graphs, right? Every path from S to T is also a path from T to S. Therefore, the ST vertex connectivity is also equal to TS vertex connectivity. Right? This you should keep in mind. Right? I will not make the distinction. You will see that in what I present now, if you think a little bit, you will see that it works for both directed and undirected graphs. So, when I say graph, it really doesn't matter if you keep in mind what kind of connectivity we are talking about. Fine. Right. So the connectivity is the vertex connectivity of ST is the minimum number of vertices to be removed so that you can disconnect all ST paths. Right. Similarly, the edge connectivity is the minimum number of edges whose removal disconnects all ST paths. Right? Okay. So there is a very interesting, so normally you might have, maybe this is the first time you are seeing max min connection, right? So this is called the Mengers theorem. The minimum, ST vertex connectivity is equal to the maximum number of internally from S2T. Right? So there is a small terminology which I will clarify now. So what does this pictorially say? What should you think about? If you have to remove two vertices to disconnect S and T, then it means that if you just remove one, there is always a surviving path from S to T. Which means that if you can go from S to T by a certain route, and if you remove a vertex, right, and it is insufficient to disconnect S and T, which means a path is surviving. So therefore, intuitively, if the connectivity is vertex connectivity of S comma T, let us say 2, then there are two vertex disjoint paths. Vertex disjoint is a bit confusing because the paths are actually not vertex disjoint because they start at S and end at T. So they are not paths which are vertex disjoint, but they are internally disjoint. There are no vertices apart from S and T which are common to the paths. Right? So let us just visualize this in a pictorial fashion.